Okay, so moving on to some more sophisticated methods. Our next method is called integration by parts. It's actually our first non-trivial method. Everything we did so far was kind of simple observations and algebraic and trig moves. So let me remind you something. Okay, there's something to say before we write this. For some reason, I don't know what reason, it's standard throughout textbooks and places in the world to use U and V as the letters for the functions when you discuss integration by parts rather than F and G. I don't know why. I'm going to follow it. So suppose you have U and V. These are now functions. Okay? And you multiply them, and you take the derivative. By the product rule, we know that this gives you U prime V plus V prime U. This is the product rules for derivatives. Right? Everybody remember? Okay. Now, we're going to feed this to the snake. So if we take the integral, the indefinite integral of uv prime, that's going to equal the indefinite integral of this side, which I can right away write using linearity as the integral of this plus the integral of this. Do you agree? But then, what is the integral, antiderivative, of the derivative? What's the antiderivative of the derivative? It's just the function you started with. Plus c, you're right. Do you agree to this? Okay? And I'm not going to write the plus c because I'm going to move one of the snakes to the other side, so there's going to be plus c's on both sides and they'll cancel. So all in all, what I get here is that the integral, and now I have to be consistent with what I'm going to write next. So I'm going to write it, the integral of uv prime equals uv minus the integral of u prime v. So this is the, you can call it a theorem. What we wrote above is the proof. But this formula follows the name integration by parts. And in fact, it's just the dual of the fact, or the dual of the formula for the derivative of a product, the product rule. Okay? And here are some examples. Okay, so remember this. And here are examples. We're on example number 9. No, here the prime is only on v. When I want to write uv prime, I write it like this. I just took the ends and moved one to the other side. Do you see how I got from here to here? uv equals the sum of these two. Then just this one, well, I wrote u before v prime, equals uv minus this. Okay. So 9. Suppose we want to do the integral of x e to the x dx. This is the integral of a product. That's usually the situation in which we'll use integration by parts. Okay? So we have to choose who's going to play the role of u and who's going to play the role of v prime. And in many cases, both can play both roles, and you just have to choose. So here I'm going to let x be u and e to the x be v prime. Okay? So what I need to find is u prime. U prime is just 1, because u is x. And v is e to the x, because v prime is e to the x. Do you agree? And I recommend, from here on, even when you become masters of integration by parts, always write this to explain what you're doing. Don't just use the formula. Write Who's u? Who's v? Who's v prime? Who's u prime? Okay. Warm recommendation. Now I'm using the formula. So the formula tells me you took the integral of u times v prime. That equals u times v x e to the x minus the integral of u prime times v. Do you all recognize the formula that we had in a blue box on the previous board? Good? Okay. Let's close the door. It's a bit noisy here. And now it's from here it's an immediate calculation. So it's x e to the x minus e to the x plus c. Good? Okay. Here's another example. Oh, something in my teeth. Okay. 10. Never eat sesame during the break. Okay. Example 10. Suppose we want to do the integral e to the x cosine x dx. So again, we recognize that this is a product of two functions, and we're going to do integration by parts. So this is going to be my v prime, this is going to be my u. And note that you can choose the other way around, because you know how to take derivatives of both, and you know how to find antiderivatives of both. It's just a matter of decision. If this is v prime, what is v? E to the x. If this is u, what is u prime? Minus sine of x. So this is the derivative of cosine is minus sine. Right? So what do we get? We get u times v e to the x times cosine x minus the integral. This minus is because of the formula. The integral of u prime v. So there's another minus from here, making this minus into a plus. And then we have e to the x sine x. Does everybody agree so far? Good? I want to keep this all on the same board, so I'll erase example 9, and we'll continue up at the top. Does everybody agree so far? We're not done, because this is still not an immediate integral. What can we do with this one? Right, we can do integration by parts again. We can give up, because it seems like we're in sort of the same mess, or we can give it a chance. Let's give it a chance. So again, I'm going to choose this to be v prime, and therefore v is e to the x. And again, I'm going to choose this to be u, hence u prime is cosine of x. So I'm doing integration by parts again. And what I get, continuing up here, first of all, this term I just carry along. So this is this. And now the integration by parts for this term gives me u times v e to the x sine x minus the integral of u prime v e to the x cosine x. Do you agree? Now we're really back where we're started. So now it really wouldn't make sense to do integration by parts again to that. Right? So we can give up. But there's actually something nice happened here. And what the nice thing that happened is, forget the intermediate step. We know that this thing equals all this minus the same thing. we can move this to the other side, so we'll get that 2 times this equals this. Do you see that? Add this entire, call this thing I for integral. This is I as well. So what we have is that I equals this. Add I to both sides. What we get is 2I equals e to the x times cosine x plus sine of x. And therefore, I itself, which is what we started with, I equals e to the x divided by 2 cosine x plus sine of x plus c. Actually, we needed the plus c here as well. I just called all of this. No, not the interval, the integral. Yeah, I just called it. No, don't call it I if it confuses you. Call it, what do you want to call it? B. B is good. B. Then we'll have to be, or not to be. Ha, 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 ha. Good? Clear what happened here? So we actually solved it. Okay. Example 11. Example 11. Suppose we want to do the integral of arc tan x. We know how to take the derivative of arc tan, right? It's 1 over 1 plus x squared. But we don't know a function for which arc tan is the derivative of. It's not an immediate one, right? It's not on the list, right? So what can we do? Right, so there's a trick here. We're going to do integration by parts. And you're going to look at it and say, what are the parts? Well, tan x is going to be one part, and arc is going to be the other part. No, can't do that. So what are the parts? Right, we're going to throw in a multiplicative 1 here. This is something we can always do. Okay? And then do integration by parts. So now do we have a choice of who's going to be the u prime and who's going to be the v? Or sorry, who's going to be the u and who's going to be the v prime? Do we have a choice? No, we don't. If you want this to be your v prime, then you have to know what v is. But if you knew what v is, you'd be done. Right? So we have to take this to be the u and this to be the v prime. And therefore, v is just x, and u prime is 1 over 1 plus x squared. Do you agree? Good? Okay, and now what we get is u times v, x arctan x, minus the integral u prime v, x over 1 plus x squared dx. Good? Just use the formula. Good? Okay, so this equals x arctan x. Didn't touch that. And now, what about this one?
The derivative of the first on top.
Right. This is a situation where it's a fraction, and on top you have the derivative of the bottom, up to a multiplicative constant. Okay? And remember we said, it's still here on this board, that when you have such a situation of f prime over f, and you're looking for the integral, please look on this board a second. When you have f prime over f, the antiderivative is ln of the bottom. Okay? So let's do that here. So we have minus ln of absolute value of the bottom plus c. And we have to fix this. There's always going to be some fine-tuning at the end. So what's the derivative of ln of this thing? It's 1 over this thing times 2x. But we don't want 2x, we want just x. so we have to throw in a 1/2 to cancel it out. And that's it. In fact, you can even say a bit more. In this case, you don't need the absolute value because 1 plus x squared is always positive, so you can replace the absolute value with just parentheses. That would be as correct. Good? Okay. So, and note already at this point that what you get is sometimes somewhat surprising, right? You got here an ln, and you got a product of x and arctan x, and look what you started with, just a very innocent-looking arctan. Okay, so when you do antiderivatives, sometimes you get answers which could be surprising or look like who knows where they came from. Well, we know how we got them. It's always a good idea to check yourself, and the easy way to do it is take the derivative of this. If what you did is correct, the derivative of this should be just arctan. Okay? And it's a good practice, a good habit to do that. Question, yes?
Can you please repeat why VA has to be the square arm for this example?
If you wanted this to be the v prime, you would need to tell me what v is. What is it a derivative of? But if you knew what it's a derivative of, you'd be done. Right? That's what you're trying to solve here. So you have to choose this to be the u and take a derivative of it, and take the other factor to be the v prime. Okay. So that was our method of integration by parts. And the next method we're going to discuss is called integration of rational functions. So as you will see as we introduce more methods, there's really no algorithm for solving integrals. It's not like I can give you a recipe book, you check your integral, if this, then do this, if this, then do this. That's not how it works. Okay? So we're here. It's not that you have sort of a recipe book to follow. You really have to kind of solve many practice examples, and using those to become more and more experienced. And then when you look at an integral, you won't try all the 15 methods you have. You'll make wise guesses as to which methods to try. Okay? And sometimes it'll work and sometimes not. The one situation in which there really is an algorithm is this situation that we're going to describe here, which is called rational functions. So integration of rational functions. Remember what a rational function is? Remember what a rational function is? It's a quotient of two polynomials. Okay, p of x over q of x, where p and q are polynomials. That's a rational function. And for integrating folks like this, we have an algorithm. Now, the algorithm is ugly. It has, you know, it's an algorithm. It has, if the situation is this, do this, and break it like that, and do that, and all with tons of parameters, and ugh. So I'm not going to write it as a theorem and write the entire algorithm. If you're really interested in seeing it, you can either Google it and go even to the Wikipedia entry or look at any textbook. I'm just going to do examples which exhaust all the various situations that we need to know. Okay, so I'm just going to do examples, and from the examples we're going to understand what we're doing. So, what example are we on? 12. Okay, so here's our first example. Integral of rational function dx. There should be a polynomial up here and a polynomial down here. The bottom one is going to be nice and friendly. The top one is going to be nice and friendly too. 2x to the power 4 minus x to the power 3 minus x squared plus 3x minus 4. Ha. Okay? The first thing you do is you check whether the degree of the top is greater than or equal to the degree of the bottom. It is in this case. And then what you do is long division of polynomials. Does everybody know how to do long division of polynomials? Is there anybody who doesn't know how to do long division of polynomials? Okay, so I'm not going to do it. Okay, if you for some reason don't know how to do it, look it up or ask. And what you get is, after long division of polynomials, is you're going to get what you get is the result of the division plus the remainder, right? So what you get is 2x squared minus x minus 3 plus 4x minus 1 divided by x squared plus 1. This is what you get. Okay? And you can check me. Just do the long division and see that you get the same thing. Okay, good. Now, the first part is just a polynomial. So for this one, it's an immediate integration. So what do we get? The antiderivative of x squared is x cubed. But the derivative of x cubed is 3x squared. And we don't want 3x squared. We want 2x squared. So we multiply it by 2/3. Clear? Are you starting to get the idea of what I mean by first write the obvious thing and then do the fine-tuning? Yep? Okay, what about x minus, we want x squared over 2. We did that already, right? Minus 3x. So all of this took care of this part. And then there's this other part, plus integral 4x minus 1 divided by x squared plus 1 dx. Good? So I'm going to leave this open-ended for now. Okay? And we'll do this. This is going to be example 15. It will come up a bit later. Okay? So just this thing, I'm going to write to be continued. Dun, 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 dun.
Oh, we can do it now.
No, I don't want to do it now. I don't want to do it now because it fits nicely in a later step. Okay? I don't want to do it now. So what does this example illustrate? Whenever you have a situation where the degree of p is greater than or equal to the degree of q, you're going to divide. And you'll get a polynomial, which is easy to find the antiderivative for, plus something of the form rational function again, but where the degree of the top is now strictly less than the degree of the bottom. Do you agree? Everybody? So if we want to know how to do integration of rational functions, all we have to know is to do long division and how to handle all possible situations where the degree of p is less than the degree of q.
Maybe equal?
If it's equal, we can still do long division. Okay? So the rest of the examples are just going to be various cases, various situations where the degree of p is less than the degree of q. If we know how to solve those, we know how to solve the general situation. So we can always...
We're going to come back to this example when we know how
Yes, we'll come back to this example. That's why I wrote to be continued. It's not to be continuous, it's to be continued. We can always do this, I mean long division. Hence, it suffices to well, I want to do examples of, to know how to handle cases where the degree of p, the top polynomial, is less than the degree of q. Okay? Clear? Good? Okay. So here's our next example. Example 13. And there are going to be, so I said handle cases where there are going to be several cases, and each one gets a slightly different treatment, and that's why there are going to be a few more examples. So case one is going to be the situation where the denominator, we have a name for it, Q, the denominator, has distinct linear factors. So this is this situation, and here's the example. So suppose we have dx over 2x squared plus 9x minus 5. So P is just the polynomial 1, Q is this polynomial, and you know how to factor a polynomial, right? There are various ways to do it. You know how to do it, right? You can either use the quadratic formula and actually find the roots, or do whatever method you want. So this equals dx over 2x minus 1 times x plus 5. So in this case, this is really the situation. There are two linear factors, and they're distinct. They're not the same. Okay? So that's the situation of example 13. Okay? In this case, what you do, you write equals, and you're going to break it up into two integrals. One is going to have just the first factor as its denominator. The other is going to have just the second factor as its denominator. And we want to know what to write up here. And the theorem, which I'm not quoting because we're only doing examples, the theorem tells you you can always do this. You can always do this. Okay? And the way to do it is called, has a name. Do you know what it's called?
Partial fractions.
Partial fractions, correct. So partial fractions. So what do I mean by partial fractions? I want to break this fraction into two parts, into two partial fractions. Okay? So this is going to be equal to this, but on the top here, I don't know what's going to be. I'm going to call one of them just A and the other just B. So 1 over 2x minus 1 times x plus 5 should be equal to some A, and I'm going to find out what that A is, over 2x minus 1, plus some B over x plus 5. And the theorem tells me you can do it. You're going to find a solution. Okay? So how do I actually perform this partial fractions method? I'm going to do a common denominator here and set the numerators equal. So what I get is 1 equals A times x plus 5 plus B times 2x minus 1. Do you agree? Okay, let's continue on the next board. So we got as far as here. We want to solve this and find what A and B have to be, and then we're going to write them here. Right? Please look at this board a second. Look here. We want to solve this to find what A and B are, and then write them here, and then continue from this step. Okay? So how do we solve this? This is an equality of two polynomials. Okay? This here is just a constant polynomial 1. In more more involved cases, it will be a polynomial, an actual polynomial, not just a constant one. And here, these are two linear polynomials. So their sum is a linear polynomial. And in order for this equality to hold, the coefficients of x on both sides have to be equal. And the coefficients, the free coefficients, have to be equal. Okay? So maybe, just the next step I'll do on this board, so you can see it. So the arrow just changed direction. So from here, I got this. And now, from here, I get a system of equations. The coefficient, which is the free coefficient, on this side it's 1. On the other side, it's what? 5a minus b. And the coefficient of x on this side is 0. There are no x's there. And on the other side, it's a plus 2b. Do you agree?
I didn't understand what you did there. What did you do?
In order for these two, do you agree that this is an equality not of numbers? It's not an equality of numbers. There are x's here. It's an equality of functions, right? Which functions? These are just polynomials. Okay? Two polynomials are equal if their free coefficients coincide. The free coefficient on this side is 1. The free coefficient on this side is 5a plus or minus b. And the coefficients of x have to coincide. Here there are no x's, so it's 0. And that has to be equal to b plus a. That's what I wrote there. And if those two hold, then these two sides are going to be equal. Good? And now I have to solve this. It's going to be a system of equations, usually a very easy one, linear equations with a and b, or in more complicated cases, which we'll see later, there might be a c, there might be more equations, but this is standard stuff. There are many ways of solving this. When you learn algebra, you'll learn methods involving matrices and whatnot. You're not going to need that here. Just a equals minus 2b, plug it into here. You can solve things like this, right? And what you get when you solve this, you get that a is 2 over 11. If you solve it, you get that a is 2 over 11. So I'm writing it here. And b turns out to be what? Negative 1 over 11. Okay? There are other ways of doing partial fractions. Other ways. You can plug in minus 5 and see what solves it. You learn different ways in different places. I'm just teaching one of them. So all this was a side calculation. The general theorem guarantees that it can be done, and this is what I get. So I'm continuing from here now. So I get, I'm going to write it as 1 over 11 integral of 2 over 2x minus 1 dx minus 1 over 11 integral of 1 over x plus 5 dx. The reason I left this 2 inside is because it's the derivative of the bottom. So I get 1 over 11 ln of 2x minus 1. And the inner derivative is precisely 2, so that's precisely that. Minus 1 over 11 ln of absolute value of x plus 5 plus c. And I'm done. So whenever q, the denominator, the polynomial on the bottom, has distinct linear factors, that's how you solve it. If, by the way, it's a polynomial that has more than 2 factors, if it's a polynomial of degree 3 and it has 3 factors, your partial fractions are going to be a over one of the factors plus b over the other plus c over the other. Okay? You're not going to encounter too many of those because we don't know in general to break polynomials of degree 3 into their factors, right? So usually you're only going to see those of degree 2. Okay? So this was this example. Now the next example.
I have a question.
Yep, question.
If like something squared in the denominator?
That's going to be example 14.
I don't know.
Okay? So this is where they have distinct linear factors. Example 14 is where q of x has a linear factor with multiplicity. So the same linear factor appears more than once when you break q into its factors. So here's an example. Suppose we have 9x minus 5 over 9x squared minus 6x plus 1. So this is a rational function. The degree of the top is less than the degree of the bottom. And this equals 9x minus 5. And it's easy to observe that this is 3x minus 1 squared. So it is a linear factor, it just repeats itself twice. Do you see that? The same linear factor with multiplicity 2. Clear? dx. And it turns out that the theorem, which I didn't write, tells you you do almost the same thing as over there. You're going to do a sort of partial fractions argument, but it's going to have a slight twist to it. It's not going to be exactly the same. And what you do, let's use the next board. What you do is the following. So I want to rewrite 9x minus 5 over 3x minus 1 squared as a over 3x minus 1. That's exactly the same as before. Plus, now it's going to be different, plus b over 3x minus 1 squared. That's the way to do partial fractions for this situation. Why? That's what the theorem tells you. We're not writing the theorem, we're not proving the theorem, we're just picking up the different cases of the method. So this is the partial fractions, the appropriate partial fractions for this case. That's the way it's going to break. So what do we get? We get 9x minus 5 equals a times 3x minus 1 plus b. Do you agree? Did a common denominator, set the numerators equal. Good? Did everybody follow? Okay. And now again, I'm going to have to solve this. So these are two polynomials with parameters a and b. If they're going to be equal, then the coefficients of x, 9 on this side, has to be equal to 3a on this side. And the free coefficients, negative 5 on the left, has to be equal b minus a on the right. Good? And the solution is a equals 3. And if a equals 3, so you get minus 3 plus 3, b equals negative 2. Good?
What of 3a plus b?
Here, because it's the coefficient just of x. B doesn't have x's. B is a free coefficient. So 3a has to equal 9. This is the x coefficients. This is the free coefficients. Okay? So once I broke it like this, I can rewrite that using these. Okay, so let's go back to the other board and rewrite it like this. So this equals integral of 3 over 3x minus 1 plus the integral of, well, minus the integral, b was negative 2, minus the integral of 2 over 3x minus 1 squared. Okay? And now, the first one is ln of absolute value of 3x minus 1. I forgot the dx's, right. We can throw them in. No, good. Remember, for us, it's just part of the notation. Okay? By the way, a small remark regarding notation. It's very important not to make up notation, especially not on midterms, but not anywhere. So this notation, this equal sign, has a meaning. It means that what's written here and what's written here are the same thing. That's what you use when you want to say that things are the same. You cannot write, for example, here, an arrow like this, because that has a different meaning, and many of you did that. Used arrows instead of equal signs. That's wrong. This does not imply this. This is not a statement. This is not a statement. This is some term, and it equals this thing. Okay? You definitely can't write something like this, and some of you even did that. Invented some funny new notation, and what does it mean?
But when we're like writing on separate lines and stuff to show like we're going from this step to this step, like it's a little neater to like show that you're going from here to here, so that you're not. If you want to throw in, this is not a discussion of integrals. Okay, this is everything in parentheses. If you want to throw in arrows to explain that you're going from here to here suddenly, you can throw in an arrow, as long as it's clear what you're trying to explain. But that's not what I'm complaining about. I'm complaining about introducing new notation inside, instead of correct notation, introducing new or false notation. Okay? That you have to be aware of. Okay? Don't do that. Okay? Very important. Okay, back to this. This was a side remark. What is the antiderivative of this? It's not ln, right? What is the antiderivative of this? What is this the derivative of? Right, it's going to be of the form, let's write, 1 over 3x minus 1 up to corrections, up to fine-tuning. Why? Because the 1 over 3x minus 1 is 3x minus 1 to the power negative 1, right? Its derivative is negative 1, 3x minus 1 to the power negative 2, which is this. Do you agree? So we have to fix it. So this is 3x minus 1 to the power negative 1. Its derivative is minus, but we want a minus, so we have to put a plus here, and the minus is going to show up from the minus from the differentiating this. So it's minus, good. 3x minus 1 to the negative 2, good. Times the inner derivative, 3. But we don't want it times 3, we want it times 2, so we need to throw in a 2/3 here. Plus c. Well, I want you to take the derivative of this, just this. You can do that. That's taking a derivative. Take the derivative of this, okay? See how it relates to this. That will tell you how to add these fine-tuning thingies here, okay? And once you do that, that's my reasoning. I don't have a better reason to say why I recognized when I saw something over function squared that it's going to be something over the function. That's the antiderivative. Exactly because I know that the derivative of this is going to have the 1 over the thingy squared as its derivative. Okay, so this is an immediate integral. For me, it's immediate. For you, it's going to be immediate after you practice this and see that it really is immediate. Okay? It can be, maybe, you know, some people can argue that there are certain substitutions that you can do here. You could. We didn't learn about substitutions yet, but it's really unnecessary. Okay, you should just be able to recognize that this is the derivative of this up to fine-tuning. Okay? Yes?
With the partial fraction step,
Uh-huh.
why don't we split up the 3x minus 1 times 3x minus 1?
The question why we do it the way we do it, relates to the theorem. The theorem tells you this is how you do it. In this case, you do this. In this case, you do it. It's an algorithm. In this case, you do this. In this case, you do this. In this case. And we're just doing it. Okay? So why? Because that's the way to do it. Okay? You're asking why not write it as a over 3x minus 1 plus b over 3x minus 1. There's no chance of that working. Because that would be the same as writing it as a plus b over 3x minus 1. Right? Call a plus b c, so it's c over 3x minus 1. So that's saying that this actually cancels out a 3x minus 1 factor. It doesn't. So that's not going to work. Okay? The reason this does work, why is this really what you need to do and what guarantees that it will work, is the theory. You have to prove it, and I'm not going into all the details. And this is not the last case. There are going to be more examples and more cases.
Can the numerator be nonlinear?
Can the numerator not... No, it's only polynomials. And if we're taking the bottom of degree 2 and the top has to be of a lesser degree, then it can at most be of degree 1. Okay? What can happen is that you can have on the bottom more factors, and then the top can have higher degrees, and then you just do the same thing. That's what I said before. Okay? If you have here 3x minus 1 to the power 3, you would have another factor here, c over 3x minus 1 to the power 3. And you do the same thing. If you have two that are the same, like here, times a different one, you would have these two plus c over the different one. Okay, so you just combine the different cases to get all the possible situations. Okay. So, the next example, and this is the last example I'm going to do today, but we are going to do a couple more examples next time and then talk about substitutions. So what example are we on? 15. So it's going to be this one, which we postponed last time. So this one. Yeah, it's going to have a title in a minute. This one wraps up the example 12 over there. Remember that we left out the end. We said we'll get back to it. So that's back to it. And the title for this one is Q does not break into linear factors. Or more precisely, Q has a quadratic factor which does not break any further. Maybe let's write that. Q, this was true, but this is not explicit enough. Q has a quadratic irreducible. That's the case of example 15. Okay? Quadratic irreducible factor. Like here. This does not have roots. Okay? And what we do is we want to have on the top, we want to have just the derivative of the bottom, because that's when we use the ln. So we want to have just 2x here. Then we would know how to solve it, right? But this is not what we have here. These are not equal, so we have to correct it. So if I multiply it by 2, now I have 4x over this. And now I have to subtract 1 over x squared plus 1. Now they're equal. Do you agree? Did everybody understand what I just did? I wanted to see this. This I know how to handle. I forced it to be that by fixing it. And now it's easy. So now it's 2 times, that's this 2, ln of x squared plus 1, we said that we don't need the absolute value because it's always positive, minus arctan x plus c. Clear? So when we have this quadratic irreducible factor, we kind of complete it to the derivative and then subtract the remaining stuff. Sometimes there's still more work needed on this. That would be example 16, which is going to be example 1 next time. Okay, so let's stop here for today and continue next time.